Hello everyone and welcome back. Today we're going to talk about how you can fit probability distributions to data. And what we're going to do is use a method called maximum likelihood estimation. So this is what's called a parametric method. So you're going to have an idea of how your underlying population is distributed, but if you do have an idea, then this can be a very powerful method. And to illustrate this, I have four samples here which were drawn from a normally distributed population, and I fit these red curves to the data using maximum likelihood estimation. So the green bars are sample data, and the blue is underlying population data. So you can see, even as the green samples are wild and all over the place, our maximum likelihood estimate fits the blue data incredibly well. So let's get into how this works, and then we'll come back and I'll show you how you can generate and fit probability distributions to data using maximum likelihood estimate in Python. Okay, so let's start with a very basic example to warm up our intuition. So here's a basic example. So what is the probability of rolling two sixes on a six-sided die? Two sixes on a six-sided die. Well, there's one outcome, which gives you two sixes out of 36 total outcomes, so that's 1/36. Now, how about the probability of rolling two sixes on a 20-sided die? Well, now there's 400 possible outcomes. The two sixes is one of them, and so I got 1 out of 400. And just one more, so how about the probability of rolling two sixes given a four-sided die? Well, of course, that can never happen, so this has a probability of 0. So now suppose somebody came to you and said, hey, I just rolled two sixes on a die. Do you know what die I was holding? Well, of course, you can't be completely sure, but there is a best possible guess, and it turns out that that is a six-sided die. So let's get into formalizing this now. So here is the definition of likelihood, the thing we're going to be maximizing. So let x1 to xn be independent, identically distributed random variables coming from a probability density function f of x, except we're going to have a family of probability density functions. So theta here is going to be the parameters of the distribution. So the likelihood function which is called ln of theta, is equal to the product as I goes from 1 to n of f of xi given theta. So you can kind of think of this as a probability. It's not a probability, just to be clear, but you can kind of think of this as xi happened given theta, and xi plus 1 happened given theta, and so both of them happen, so you have to multiply them together. And now, this is going to be a long product, and a lot of times probability density functions are really small numbers. So if you have like 100 pieces of data, and each of these is like 0.01, you're going to get a vanishingly small number. So what you actually end up using in practice very often is called the log likelihood function. So the log likelihood function is just the log of the likelihood function. So log of the likelihood. And here's the important part. This turns that product into a summation, which tends to have more favorable numerical stability. So log of f of xi theta. Okay, so our goal is, given observations x1 to xn, maximize ln of theta, the likelihood. And here is the bit about log likelihood. So log is a strictly increasing function. That means if x is less than y, log of x is less than log of y. So that maximizing the likelihood is equivalent to maximizing the log likelihood. All right, so let's do an example here. Let me remind you that the uniform distribution on the closed interval AB has the probability density function given by one over b minus a if x is between a and b, and 0 otherwise. So with this in mind, here's an example. So we have a uniform random number generator which returns a random number uniformly in an interval AB closed. It gives us in four rolls -1, 1, 1.5, and 2. What is the maximum likelihood estimate for A and B? So here's the parametric part about maximum likelihood estimate. We're assuming our data is uniformly distributed. And now, how is it uniformly distributed? Well, let's just take a look at the data here. It gave us back -1, 1, 1.5, and 2. And the distribution is going to be a horizontal line straight at 1 over b minus a. So what we do is you can imagine these little vertical lines popping up. And that vertical line is the likelihood of this occurring. So again, it's not the probability in a continuous distribution. The probability of any one event occurring is 0, but you can still talk about the likelihood. So this is the likelihood of 2 given theta. Okay, so with all this in mind, what is the likelihood of the data along with theta? So theta here are the parameters of the distribution, so it's A and B. Well, you can imagine if this line doesn't encompass the numbers given, the likelihood is 0. So it's 0 if A is greater than -1 or B is less than 2. And otherwise, the more you increase the size of A and B, the lower this line gets. And your answer is going to be 4 times 1 over B minus A. So the likelihood of 2 theta, for example, is 1 over B minus A. You multiply them all together. So what's the maximum likelihood estimate? So our maximum likelihood estimate, very similar to the case before, is theta is equal to, let's be more precise, A is equal to -1 and B is equal to 2. So the distribution is uniform on -1 to 2 inclusive. Great. So now let's lead into our experiment that we're going to run in Python. So here is the example we'll run with. So we discover a new orange. new species of orange. So from our history, we know that weights of basically all fruits are normally distributed. So we assume the weights are normally distributed. Weights of this orange are normal. But which normal distribution? Well, a normal distribution has two parameters. They are mu, the mean, and sigma, the standard deviation. So here's a fact, and if you're interested in the proof of this fact, I'll do it at the end of the video. But it's just, I think, a very nice fact. The maximum likelihood estimate for mu and sigma is given by, in this case, so for normal distributions, just to be clear, the sample mean and the standard deviation. So this is the uncorrected standard deviation. Sorry, this is an uncorrected sample variance, which you could take the square root of to get the standard deviation. So in other words, if you want to know the maximum likelihood estimate, you could calculate all of these likelihoods and let your normal distribution slide around, and that's incredibly computationally expensive. Or you can calculate the mean and the standard deviation, and that's just what we'll do. All right, so here we are in the Jupyter Notebook. So like I mentioned, we are going to be using maximum likelihood estimates to fit normal curves to samples of orange weights. So I'll start off with some imports. We're going to be using NumPy. It's going to provide us with a couple helpful functions. Pandas is what we're going to be using for data manipulation. Matplotlib is going to be used to plot our outputs. And most importantly, we have Scipy stats here, and that is going to provide all of our curve fitting. So let's go ahead and import all of those. All right, so let's go ahead and read in the data. So my data frame df is going to be pdpandas.readcsv. I have this data saved as citrus.csv. So, okay, I now have the data in this data frame. So let's also take a look at the first few rows. So helpful way to do that is df.head. And that'll give you an idea of what we're looking at. So we have 6 columns here, and we're mostly interested in the weights column here, and we only want oranges. So let's take a look at what's in this name column. So what you can do is df of name.unique, and that'll give you all of the unique entries in the name column. So we have oranges and we have grapefruits. We only want oranges. One way to do that is to filter. So, and we'll do 2 at once here. So I want my data frame, and you can just put in the condition you want in here. I want where the name column is equal to orange. And then I want just the weight column here, so I can just specify just the weight column. And let's also take a look at some statistics here, and a helpful way to do that is the describe function. So there we have it. This now contains only oranges and only the weight column. I have 5,000 entries. The mean is about 152, 153. And the standard deviation is 18.66, which is obviously going to be relevant when we start fitting curves. So let's go ahead and fit a curve to this whole data here, so we can just make sure it's reasonable to assume that our data is normal. So let's go ahead and plot all of our data in a histogram. So plt.hist, I'm going to plot my orange weights. The bins is the number of bins in your histogram. I'll set that equal to 30. This next parameter is important. I'm setting density to be equal to true. And what that does is it's going to scale your histogram so that it's a probability density function. And this is going to be very useful for when we compare it to the fitted probability density function. And we'll go ahead and set the color to be blue. Okay, now let's fit the normal curve. So like we said before, a normal curve is completely determined by its mean and its standard deviation. So I'm going to have a mean and a standard deviation, and what's going to return that for me is stats.norm. That's all the normal distribution stuff inside of Scipy stats. And I want to fit this to the orange weights. So that's going to return two parameters, which are the mean and the standard deviation. All right, so now for plotting the curve, what we're going to do is set our left and right bounds and then take a bunch of slices in the middle in order to get an understanding of what this curve looks like. So the min value and the max value is going to be the minimum of the orange weights and the maximum of the orange weights. And next, I'm going to use NumPy's linspace function to get these slices. So np.linspace, you give it a min, which is xmin, give it a max, xmax, and then you tell it how many slices you want to make, and I'm going to set it to be 100. If you set this number too low, your curve is going to come out all jaggedy. So, all right. Now we can get our y values. So I'm going to call this PDF fitted. It's going to come out as stats.norm.pdf. And what this function does is you give it a bunch of x values, x, and then you give it a normal curve. So it's going to be specified by a mean, which is under the variable loc. So loc is mean, and a standard deviation, which is under the variable scale. Scale is standard deviation. And so this is like an ND array of x values, and it's going to return an ND array of y values. All right, so let's go ahead and plot this now. So I give it the x values, I give it the y values, which are the PDF values, and we'll set the color to be red. And then we'll go ahead and show this. All right, so there's our fitted curve, and there's all of our data. And as you can see, it lines up pretty well. So this is a good assumption that the data is normally distributed. So let's go ahead and now take some samples and fit some curves to the samples and see how it compares to the population. So let's start off taking a sample. So the sample is orange weights dot sample, and you can specify how many samples you want to take. Let's go ahead and take 50 samples. And we'll fit a normal curve as before to now this sample. All right, and we'll do some plotting. Let's plot all of the data and also the sample data. So we'll plot the orange weights again with 30 bins. We'll set density to be true, and the color to be blue. And I'm going to be plotting multiple histograms here. So I'm going to set an alpha value, a transparency value of 0.8. Okay, and we'll do the same now for the sample. Plot the sample in green, and Now let's go ahead and again plot the normal distribution, but now it's fitted to the sample. Okay, so I'm going to copy and paste all of this as before. Keep in mind now, mean is now the mean of the sample, and standard deviation is now the standard deviation of the sample. So let's take a look at what this looks like. So that one actually didn't perform too well, but nevertheless, it's a really, oh, I only did 50 samples. Let's take 100. Nevertheless, even with 50 samples, you get a pretty good understanding of what's going on here. And with 100 samples, we could run this a couple times, and well, the third time came out really well, but all of them gave us very good information as to the underlying population. Okay, now, as we mentioned before, this curve is fitted using maximum likelihood. So you maximize either the likelihood or the log likelihood. So let's just go ahead and see how you could get the log likelihood of this fit. So I have the mean and standard deviation again. I'm just going to refit this so we have everything in one place. So that's the fit of the samples. Okay, our PDF values now are again going to be stats.norm.pdf of sample. Location is the mean, and the scale is the standard deviation. Okay, and now we can go ahead and compute the log likelihood. So the log likelihood is equal to, okay, so I want to sum up a bunch of stuff. np.sum is very helpful for this. And I'm taking the log of the PDF values. So remember, this is how we compute the log likelihood. You get all of the y values of the PDF, you take the log of them and add them together, and let's see what we get. PDF. And we get this large negative number here. So you can't actually really interpret the log likelihood. It's not necessarily meaningful. The important thing is that this was maximized among all other possible fits. So there it is. Okay, and the last thing I want to do is just run the experiment 4 times all at once and plot all of the outputs. So I just have some code I've already written here. So all this does is run the experiment 4 times. So you take a sample in each loop, and then you plot it, and then there's some messing around with matplotlib to get it to align nicely. Not particularly interesting, so I just have it written out here. And there we have it. That's 4 fits, and you can see all of the different performances. So this last one seems to not have performed so well, but all of them do pretty well, given that we're only sampling 100 out of 5,000 data points. All right, so let's go back to the written stuff. And if you're interested, we could see that maximizing the log likelihood for the normal distribution amounts to just picking out the sample mean and the sample variance. Let's go ahead and sketch out a proof of this. So let's recall a couple facts. First of all, let me remind you that the likelihood function is given by multiplying the probability density function for that given theta over each of your observations xi. And I'll also remind you of the probability density function for the normal distribution. It's given there. Hopefully it looks a little familiar. So let's go ahead and start. Our first observation is going to be that when we multiply together these densities, it actually doesn't look too terrible. So given our mu and sigma squared, the likelihood function is given by 1 over square root of 2 pi sigma squared to the n times e to 1 over 2 sigma squared times that summation there. So what's going on here? All that's going on here is we're multiplying together all these numbers. We're multiplying together n of them. And that 1 over 2 pi sigma squared is present in all of them, so it gets raised to the n. And then we have a multiplication of a bunch of exponentials. And remember that exponentials have the property that when you multiply them, it's the same as adding together their exponents. So that product turns into a summation in the exponent. Now, that also helps us calculate the log likelihood. So the log likelihood is given by that expression there. And all I did there was apply ln to the likelihood function. And it turns the product into a summation, and it brings the exponents down. Okay. So now what we're going to do is maximize this log likelihood. So this is a 2-parameter maximization problem. So we're going to use some calculus. The shape of ln of theta looks like, so the data is fixed, and we're varying the mean and the standard deviation. So just as a example, let's say that's the variance sigma squared, and here's the mean, and what we'll have is some rising curve like this, and we'll get some shape like this here. I'm not claiming it looks exactly like this, but this should illustrate the point of what we're going to be doing here. What we want to do is find this maximum point, and if you remember from calculus, what you need to do is find this point where the partial derivative with respect to mu is equal to 0, and the partial derivative with respect to sigma squared is equal to 0. So we're going to take the two partial derivatives of the log likelihood and set them equal to 0, and that will be our maximum likelihood. So let's go ahead and do it. So let's first do the mean. So what is the partial derivative with respect to the mean of this log likelihood? Well, actually not that many terms involve the mean, so this is pretty easy. The first two terms have partial derivative 0, and the last term is a simple calculation. So what happens is that squared comes down, and then the chain rule says you need to multiply by -1. So I get 1 over 2 sigma squared times the summation as I goes from 1 to n of xi minus mu. The squared came down. And came down to cancel that too, of course. So when can this be 0? If the partial derivative with respect to this mean is equal to 0, well, then what we have is 1 over sigma squared times the sum as I equals 1 to n of xi minus mu is equal to 0. Okay, so the 1 over sigma squared doesn't matter. It's multiplied, and it can't be 0. So instead, we have the summation term. Well, in the summation term, that mu is getting added together over and over again. So what we get is the summation as I goes from 1 to n of the xi, and I can pull out the summation of the mu's, so minus n times mu is equal to 0, and so I'll get that mu is equal to the summation as I goes from 1 to n of the xi's over n. That's what we thought. Great. So the only time when the partial derivative with respect to mu is 0 is when mu is equal to the sample mean. Now let's take a look at the variance. So I'm going to need to look at the partial derivative with respect to now sigma squared. There's some potential for confusion here. Sigma squared is our variable. It's not the square of our variable sigma. So the partial derivative with respect to sigma squared of this log likelihood. And this turns out to also not be too bad. So the first term doesn't have a sigma squared. The second term is just an ln, so I get minus n over 2 sigma squared. And that last term just has a sigma squared in the denominator. You could think of that as like a 1 over x. So I'll get a plus 1 over 2 sigma squared squared times the summation as I goes from 1 to n of xi minus mu squared. All right, so let's do some manipulation here. I am going to factor out a 2 sigma squared. So factor 1 over 2 sigma squared. And what do I have left? So I'll have a 1 over 2 sigma squared of a minus n and a plus 1 over 2 sigma, sorry, not 2, sigma squared times the summation as I goes from 1 to n of xi minus mu squared. All right, so I want this term to be 0, and I can control the sigma squared. So what does this sigma squared have to be? Well, essentially, I want this inside to cancel. I want this inside to be 0, so I want 1 over sigma squared times the summation as I goes from 1 to n of xi minus mu squared to be equal to n. Because if I have this, then that term on the right equals n, and that will cancel out with this minus n. And from here, it's straightforward. We see that sigma squared is equal to the summation as I goes from 1 to n of xi minus mu squared over n. Yep. And there we have it. That's our sample variance. All right, so that's all I have for y'all today. Thanks for watching.